Hello and welcome. This is going to be lecture number 12. Go ahead and put that number and the date at the top of your notes. We'll go ahead and get started. This lecture is going to be all about balanced and unbalanced forces. All right, so we'll start with Newton's second law. Newton's second law can be boiled down to a very simple equation. You need to memorize this one. It is simply force equals mass times acceleration. F equals ma. If you can just remember that simple equation, you have memorized Newton's second law. So what are the units of force? Well, we can get that from Newton's equation. Force equals mass times acceleration. So F is force. Mass, the units is going to be kilograms, and acceleration, the units will be meters per second squared. So if I multiply kilograms times meters per second squared, the kilograms will go to the top and I'll get kilogram meters over seconds squared. Well, that big unit there, we're going to boil down to a single letter N, which stands for newtons. So what is a force? A force is any push or pull. Think about it as a constant amount of pressure that's going to cause some acceleration. And however long this push or pull lasts is however long that acceleration will be allowed to speed up an object. 1 Newton is the amount of force necessary to take 1 kilogram and accelerate it at a rate of 1 meter per second squared. So 1 Newton will take 1 kilogram, which remember is about 2.2 pounds, and get it moving at a rate of 1 meter per second squared. That's an increase of roughly 2.2 miles per hour every second. So one thing we've said about gravity so far is that the acceleration caused by gravity is constant. The acceleration is always equal to 9.8 meters per second squared. But now if we take that acceleration and put it into F equals ma, we'll see that the force of gravity is actually proportional to the mass of an object. So the acceleration is always going to be 9.8, but we still have to multiply it by the mass to figure out the force of gravity. So if we have 5 kilograms of weight, the force is going to be equal to 5 times 9.8. The force is going to be equal to, let's do that in a calculator, 5 times 9.8 equals 49 newtons. If this 5 kilograms is to drop, it is going to accelerate at 9.8 meters per second squared, but the force of gravity just pulling on it at all times is 49 newtons. What if we have, let's say, 42 kilograms of mass? Well, the force equals 42 times 9.8. 42 times 9.8. The force is 411.6 newtons. So the force is going to be stronger on heavier objects. That does not mean that they will fall faster, though. All right, so that is the force of gravity. Now let's talk about this concept of net force. The idea of net force is to represent multiple forces with a single force vector. So forces are vectors. They have a magnitude and direction, and we can just add them together to find one net force. So we can represent multiple forces with a single force vector with this idea of net force. All right, so let's talk about a really common occurrence, and that's any object that is sitting in a place not moving. So we could think about a book just sitting on a desk. Here's our book, and it's sitting on a blue desk. And although this book is experiencing a force due to gravity, it isn't accelerating. There's a force that's trying to pull it down, and that force is called gravity. But another force is pushing right back up on it, and we're going to call this the normal force. All right, anything that's resting on another object is experiencing the normal force of that object pushing back. This is the desk pushing back on our book. And that is the normal force. Notice in this scenario, the net force equals 0. Normal force plus gravity is 0. They cancel out, therefore our book doesn't move. Here, we'll label it as a book. All right, if a force is anything that can change velocity, then friction is definitely a force because it slows things down. And when you slow down, your velocity is changing. So something important to know about friction is that it always points in the opposite direction of motion. It always points in the opposite direction of motion. And it comes in a couple different types. There's static, there's sliding, and there's rolling. All right, static is for things that are not moving. So this doesn't mean they're not experiencing any forces. Lots of things that are not moving are experiencing lots of forces. It just means that the net forces are 0. So if I push on my desk, the desk doesn't move because the force of friction between the desk and the floor can match the force that I'm pushing on it. Sliding, this is for things that are sliding. They are moving. And specifically they're sliding, and rolling is for wheels and other cylinders that are also moving. But the point of contact is actually static, but we do pick up a little bit of friction because the rolling object has to kind of bump up and down the different imperfections of whatever it's rolling on. So if I've got a wheel going down a road that's a little bit bumpy, it's going to bump up and down as it goes, and that's consumes energy to do it and slows down our forward motion. Next, let's talk about this idea of a free body diagram. So if we've got a very complex situation, like maybe we're going to shoot a person out of a cannon, we don't want to have to worry about how the force is going to impact every tiny little part of our person, so we boil our person down to a single point. We call that point the center of gravity, which is sort of an average of all of the mass of that person. Then we can act like all of our forces are acting on a single point. So we keep that point in the middle, and then we can say maybe we've got a lifting force as they get shot out of the cannon. Maybe there's always going to be a gravitational force. Maybe they were already running forward, so they've got some air resistance pointing backwards. And maybe they're still trying to pick up some speed, so they've got some forward pushing force. A lot of things are happening. But all we see in our free body diagram is only the force vectors. So they're just all of the force vectors acting on a single point. We don't need to draw the actual object in the middle. It just makes it too messy. All right, now for a kind of tricky word problem. so that we can add in a little bit of math to our discussion of forces. So let's talk about a 20 kilogram sled that is being pushed with 150 newtons of force. And as a result of this force, it is accelerating at a rate of 2 meters per second squared. What is the force of friction pushing back on the sled? So let's go back to our most famous equation. Force equals mass times acceleration. And let's plug in just the mass, which is 20, and the acceleration, which is 2, to figure out what the net force is on this sled. So 20 times 2, the net force is 40 newtons. All right, so 40 newtons are available to accelerate the sled, but we pushed with 150 newtons. So what happened to the rest of those newtons? Well, they were opposed by the friction force of the snow on the treads of the sled. So I'll just do my 150 minus the 40 to get that we have 110 newtons of friction. And I think it would be totally acceptable to make this a negative 110 newtons of friction because it's going in the opposite direction of our motion, which is with this 150 newtons. All right, we'll call that good for this lecture video. I'll embed a few more questions here, and have a good rest of your day.